Hello, everyone. Hope you're doing well. I had this lame idea of having some music involving circles or going round and round or anything to intro this, but I could just say that this video is going to make your head spin, because that's just as stupid. Anyway, this video is all about circular motion. It's a general overview, and it's an algebraic approach. No need to throw numbers into this, but a general problem-solving strategy. We will cover horizontal circles with friction. We'll cover a variety of vertical circles, and we will also discuss conical pendulums. Those are the things that we focus on in class. So if there's one that you're looking for in particular, fast forward through this video to find the one you want. All right? We will start with horizontal circles with friction. I tend to draw my horizontal circles like this. It's because it's on a piece of paper that's facing this way, and we got to draw it horizontal, and it's the best I could do. By now, you are a dynamics expert, and you should know that you're going to be drawing a free body diagram. This is a car going in a circle, we'll say, or a bike going in a circle, or you running in a circle due to friction. As you know from our most amazing class, the main concept for circular motion, which I can throw right here, is that the net force is towards center. I mean, if you don't know that after day one when we covered this, talk to me about that, because that's not good. And if the net force is towards center, that means the acceleration is also towards center, because F equals ma, sillies. All right, that's the most important concept. That's a terrible W. That's my downfall. I can't draw W's. Anyway, let's put a little friction towards the center. After that, not much changes. We do a little sum of the forces X, sum of the forces Y. So for this particular problem, I'm going to do the sum of the forces that cause the mass to move in a circle. The acceleration towards the center, AC, or A centripetal, is the velocity squared divided by the radius, so v squared over r. I tend to write, instead of writing ma, I just go directly to v squared over r. You can do whatever you would like. But when I see this, when I see v squared over r, that is screaming at me, hey, this means circular motion. So what forces are causing the mass to move in a circle? The only one we have is friction, which is mu times the normal. And that is what's causing the mass to move in a circle. By now, I also think you know that the sum of the forces in the y here, this vehicle or person or bike or whatever, is not accelerating vertically, so we simply have that the normal force is equal to mg. And if we sub that puppy in, we get mu mg equals mv squared over r. There are two terms here, both of which have mass. Therefore, the mass divides out. And you're left with v squared equals rug. I don't want to write down because I don't want anybody to remember it, but AP people, if you're watching this video, I'll write it down now. V is the square root of rug. Phys 1, do not memorize this. I mean, it's good to know for multiple choice, but if you were to just use this on a test, you wouldn't get credit. AP Physics, though, great for multiple choice, okay? Good to know. It's quick, it can be helpful, and I'm going to erase it, and that's that. Now, I am not a nice person. We all know this by now. So if this was a test question, I would probably add some additional force here, like, I don't know, 200 newtons. It's random. Now, when I do the normal force, I get Fn plus 200 newtons minus mg equals 0, or the normal force is equal to mg minus 200 newtons. And I'm just doing this as an example to prove something, because then when I substitute this in here, the difference is that now I get mu times the normal, which is mg minus 200 newtons, equals mv squared over r. Do you see an m in every term here? Because I don't. And if you don't, then it doesn't divide out. Just be aware of that. All right, so that's horizontal circles with friction. All right, let's do a little vertical circle, shall we? Little verticals. How do you spell vertical? Is that right? I should know these things. Vertical circles. All right, we have a variety of them. So let's say that you are on a Ferris wheel going over the top of a hill, or on a Ferris wheel at the bottom of a hill. You know what a Ferris wheel is, I think. It's this thing that goes around, and there's all these seats and stuff that go around. Seat, seat, seat. I don't know what I'm drawing here, but you get the idea. It goes around in a circle. Ferris wheel. Look it up. All right. Let's draw a free body diagram of you on this Ferris wheel. Well, at the bottom of the Ferris wheel, you have the normal force and you have gravity. We're not dealing with friction in vertical circles, okay? And hey, at the top of the hill, you have normal force and you have gravity. Wow, these look exactly the same. However, take note of this. Very important. Toward center is the positive direction. That is the rules for these problems. Deal. There are other ways to do it, but trust me, this is like the most important. Which means positive is towards the center of the circle. So this is positive, this is negative. Terrific. Well, here's the center of my circle here. So down is positive. Anything towards center is positive, which makes mg positive and the normal force negative. That's okay. I've heard other people say they visualize the circle, and if a force is anywhere inside the circle, it's considered positive, and if it's outside the circle, it's considered negative. If that works for you, lovely. I like the way you're visualizing it. Whatever works for you. After this, let's do a little bit of quick math here. We have a little forces that cause the mass to move in a circle. Remember, towards center is positive, so we have mg minus Fn equals mv squared over r. For the one on the bottom, we can sum the forces that cause this mass to move in a circle, and we have normal towards the center, positive, minus gravity, and that causes the mass to accelerate in a circle. Simple as that. Perhaps, I don't know, we're upside down at the top of a circle. Okay, so you're on a roller coaster going super duper fast. That is the assumption. Technical term, super duper fast. Well, there's still gravity, which is mg. But if you're going really, really fast, the normal force actually pushes down. Okay, if you're going really slow, technically, you'd be falling out of your seat and your seatbelt would be holding you up. But for the problems we do, we can assume that we're going fast enough that the surface is actually pushing down on you. Similar, like here, if you were going really, really fast over the top of a hill, like the second hill on Nitro, after you go down that first big hill, you come up over the second hill, and you get whipped back down. You're going so fast that if it wasn't for a seatbelt, you'd go flying away. And in that case, the normal force would actually act down. But for our purposes, we could just assume that the surface is acting perpendicular on us. So if we're above it, it points up. If we're below it, as in this case, it points down. I would like to add that toward the center of the circle is positive, which means both of these forces are positive. Fascinating. So I'm going to sum the forces that cause this mass to move in a circle. They both are towards the center, so it's Fn plus mg equals mv squared over r. And that's basically our vertical circles. There is another example, but I want to pause sort of a moment right here. I've been doing this, I don't know, about a month. If a month goes back to 2005, I've been doing this for a while. And every year I hear the same question. How do I know when it's mg minus Fn or Fn minus mg or Fn plus mg? Why are you trying to remember when it's what? That is the super wrong approach. Do not try to memorize. Is this the one where it's that? I don't know. Like after 18 years or 17 years, I don't even know. I have to stop and think because it's irrelevant. So I don't know. Don't memorize. It's ridiculous. If you try to memorize 3 different scenarios, you're doing way too much work. Can I make a strong suggestion? Draw a free body diagram, towards center is positive, create the math. That's it. Then you don't have to memorize anything. Just draw a free body diagram. Also, don't try to memorize free body diagrams. That's insane. You've done a lot worse than this before with forces at angles and crazy substitutions. This is 2 forces. Gravity's always down. Hint, hint. The question is, what else is there? All right, a few more examples of vertical circles. I hope I made my point about not memorizing. You could have something on a string, so like a mass, like a ball here on a string at the top or bottom of a circle. So there's my string. And if I were to draw a free body diagram in this case, tension is towards the center. Gravity points down. And I don't want to spend too much time on this, but towards the center is positive. So these are both positive. And here towards the center is positive, so positive, negative. And if I were to sum the forces for these scenarios, I don't know if you can hear that in the background, causing the mass to move in a circle, you have tension plus gravity causing the mass to move in a circle. And at the bottom, if you sum the forces, you have tension minus gravity. Like, see, it seems so hard to memorize what's what. Just draw the free body diagram and let it help you create the math. Last thing, I feel like I'm squeezing here, so I'm going to move down a little bit. Last thing, the term weightless. Not a fan, but what if you're weightless at the top of a hill? You'd be going under the hill or, whoa, hey now, that just disappeared. Or over the hill, that's probably going to show up somewhere later. It doesn't matter. If you hear the term weightless or just enough speed to make it around, this will be discussed later at the end when we wrap this up. That means the only force acting on you is gravity. It means no normal. It means only gravity. That's why I have an issue with it. Weight is a force. It's the force of gravity. Weightless implies no gravity, but it's more a feeling. You feel like you're super light. And in this case, if you sum the forces that cause the mass to move in a circle, you've just got mg equals mv squared over r, and yes, the mass divides out. AP, worth memorizing that the minimal speed to make it around, or the weightless feeling, v is the square root of rg. It's very helpful. Okay. Last thing we'll do is something called the conical pendulum. It's like the swing ride at Bowcraft. Do you remember Bowcraft? I don't know. Some of you are old enough, and depending on how long this video is on YouTube and how long I teach, some of you are going to be like, what the hell's Bowcraft? Anyway, any swing ride where you're going in a circle and you're on a string or a chain or something like that, your free body diagram is pretty straightforward. There's a rope or a chain, some kind of tension, and gravity. That's it. Okay? Sorry, this is known as the conical pendulum. Conical, because it traces out the shape of a cone. So it's conical. Education. I'll stop talking. All right, still, we have a free body diagram. It's moving in a horizontal circle. I'm going to sum the forces that cause the mass to move in a circle. Now, gravity is acting straight down, so it has nothing to do with this horizontal circle. It's the tension. Tension's at an angle. That's cosine. Causes the mass to move in a circle. In the y-axis, if you've been on this ride before, you are not accelerating vertically up and down. You are at the same height most of the time. So when you sum the forces in the y, it's 0, and you have the tension force acting at an angle minus gravity equals 0 newtons. Just going to rewrite this so it looks a little prettier with the mg over here. Okay. Not much else to be said about this. This is a conical pendulum every time. There's not much I can do with it. That's it. That's it. That's all there is to it. However, you should take note of the fact, you've seen this kind of stuff before. We have a tension force and an angle. Tension force and an angle. It almost reminds me of those equilibrium problems that we used to do. In this case, you often have two equations, two unknowns, which means you're going to have to, not always, but often, two equations, two unknowns. So you're going to have to do, by now, either substitute if you'd like, or you can isolate and set equal. And also, if you don't know the angle or the tension, odds are you are going to end up with sine over cosine at some point, which will become tangent. We've done this in class. I'm not going to review it here, but use the notes from class if you'd like to. All right, peoples. That's basically it. Let's do a quick review if I can find it. Sorry, this video is a little long, but we did cover a lot. All right, ladies and gentlemen. Bottom line. We've been doing dynamics problems for a long time. You know where to start. You draw a free body diagram. The new thing is that towards the center is positive. It's worth labeling. I've seen people put a positive symbol right next to the force to remind them what's positive. And instead of writing some of the forces that cause the mass to accelerate, we know that the acceleration towards the center is v squared over r. So I just immediately go, sum of the forces is mv squared over r. Aside from that, pay attention to the words weightless or just enough speed to go around. That means there's no normal force. There's only gravity. And I cannot stress this enough. Seriously, every year people do this, and I don't know why. Don't memorize. Don't be that person that after I just said don't memorize, the first thing you say is, well, how do I know if it's Fn minus mg or Fn plus mg? I don't know. I don't pay attention to those things. I draw a free body diagram. I then use that free body diagram to create an expression, and I solve. I don't worry about if it's this or that. Please don't be that person. I think I've made myself very clear. Clear as 3 out of 5 stars. Wouldn't change a thing.